When should you use the mean instead of either the median or the mode? Well, quite simply, the answer is whenever you possibly can. I say this because the mean is the preferred method. It's the preferred method specifically for measuring, central tendency. Now, why would that be? Well, I'm going to lay out some of the basics about the mean here, and they fit into two basic categories. So there's the good stuff and there is the bad stuff. And the reason that it's preferred is because of the one simple good characteristic of the mean. The mean uses every single score. When you're finding the mean, you use every single score in the distribution that you're trying to describe. And remember, the whole idea of a measure of central tendency is to describe what's typical of the entire distribution. So the mode and the median both don't do that. The mode chooses a single value, and the median only looks at the lowest and the highest values, whereas the mean uses every single score in the distribution. This happens, you can see right away in the formula. Let's say, for example, I'm looking at my population mean. The population mean is the sum of x over n. It's the sum of every single one of my scores divided by the total number of scores. So all of the scores get involved in this calculation. If I change a single score, then I'm going to end up changing both the top and the bottom. I'm going to change everything about how the mean is calculated. So this is why the mean is the preferred method. It encompasses, or it incorporates, every single score in the distribution, and we're trying to summarize the entire distribution. Now, there are a couple of drawbacks to using the mean, or rather I should say there's some characteristics about the mean that make it a bad choice in some situations. And so one of them is that the mean is too sensitive to extreme data. What do I mean by that? Well, let me give you an example. Let's say that I have a simple data set. I'm looking at people's salaries. Let's say one person makes 80,000, another person makes 90,000, another person makes 100,000, and then somebody makes $1 million. Now, if I were to take the average of these values, I would have to add them all up. And so what would I get there? I'd get 80 and 90, that makes 170. This is 270. This is a million, so it would be 1,270,000. That would be my sum of x. And if I then found my mean, let's say that this is a sample that I've taken, or I'll keep it simple, I'll just call it a population. My population mean requires that I know the sum of x divided by the total number of values in the population. It's a very small population here, just 4. And so I've got 1,270 over 1, 2, 3, 4. And so let's have a look and see what that's equals to. 1,270,000 divided by 4, it gives me 317,500. So this is 317.5 K, 0.5 thousand. Now, this value here isn't exactly what we would call typical of this entire distribution. In fact, there's one value that makes, or there's one person who makes far more than that, 3 times as much basically, and there are people, the rest of the distribution, or everybody else in the distribution, makes far less than this supposedly typical value. In fact, they make less than a third of this supposedly typical value. So in other words, this supposedly typical value is not typical at all. The mean fails in a situation where we have a cluster of data and then there's an extreme outlier. And it doesn't just have to be one extreme outlier. It could be that I have hundreds of employees and maybe only dozens of these extreme values. This is what we call a skewed distribution. You might, if you were to graph this out, salaries, you would see that there is a high frequency of low salaries, and then it sort of skews. I guess I need to make a bit of space here. And then the distribution trails off towards less and less and less employees that make higher and higher and higher salaries. So here would be no salary, here would be extremely high salaries. When you have a skewed distribution like this, the mean is not a very good choice. What happens is the mean gets pulled away from where the bulk of the data is. The mean gets pulled towards where the extreme data is, or where that skewed end is. Another situation where the mean would not be appropriate at all is when you have nominal data. The mean cannot be used with nominal data. In fact, it can't be used with nominal data or ordinal data. There's a little bit of debate about that in your textbook, but essentially in your course, nominal and ordinal data, you're not going to want to use the mean. The mean requires that you perform calculations. You have to sum up all of your values and then divide by the number of values. Well, what if you had nominal data? What if you did a survey where you asked people, what's your favorite color of Smartie? And some people said red, and one person said blue, and so on. How are you going to add up these values to get your sum of x? That doesn't work out. So you can't find the mean for nominal data. If you had ordinal data where, let's say you don't have any numbers at all, let's say you've asked people, you're taking orders to go out and buy coffee. Some people want smalls, some people want large, one person wants an extra small, and so on. If this is your data, it can be put into order, but what you can't do is you can't find the sum of x. So it doesn't work out. If you can't perform calculations with your data, so if you have nominal or ordinal data, you can't perform calculations, and therefore you cannot use the mean, because the mean requires that you use this formula. In every other situation, though, the mean is by far the best choice. So whenever we have regular lists of data that is not nominal or ordinal, and data that does not have extreme outliers, then we're going to want to use the mean, because the mean uses every single score in the distribution, and that's what we're after in a measure of central tendency.